So we like to walk this path to the future, the path of the unknown. It's called an adventure in the future. And the most important is to ask a question. Which questions are we going to ask to Mother Nature? Which questions are we going to answer? You should realize that this provides us the challenges for our young people, our students, the dreams for the people, opportunities for society and industry. Indeed, it's an adventure in our future. And often, ladies and gentlemen, to try to answer this question, to enjoy the beauty of the scientific world, we get completely lost. Lost in this beautiful garden, which is called the Garden of Science and Knowledge. And we find these question marks that we have no idea that we should ever ask those questions. These are usually the most interesting questions. We hit upon new discoveries, new insights. Of course, we make failures, but don't be afraid to make failures, because we learn a lot from our failures, and that brings us to the future. Let me go back in time a little bit to this gentleman, the Wright brothers. I often get the question, why do we need molecular machines? Why do we need nanotechnology? Why to work on this small scale? I try to explain today. The same question was asked to the Wright brothers. Why did mankind need to fly? If God wanted us to fly, he would have given us wings. Nobody would have expected that 100 years later we would fly an Airbus or Boeing, you know, that I used yesterday to come to your country. Nobody would have predicted at that time. Of course, we admire the flying bird. Isn't it beautiful? But this machine here, this Boeing or Airbus, is completely artificial, completely synthetic, built by physics, chemistry, material science, computer science, engineers in particular. 3.5 million parts, all artificial. But it does its job very beautiful, eh? Once again, we admire the flying bird. But try to fly from Europe to Jakarta with a bird, with 400 people, 1,000 kilometers an hour, 10,000 miles. It does not work, eh? And the flying principle of your plane is not the flying principle of a bird. But 100 years after the Wright brothers, ladies and gentlemen, we cannot build a bird. Our friends in biology, they cannot build a single cell of the bird. Not even one of the machineries of the bird. There is still a long way to go to discover and to invent. So I suppose you all have a smartphone, or at least most of it. This lady has, I can see. Beautiful. We enjoy. But the question is, which fundamental scientific discoveries, which new insights were made to make this possible? We should not forget, developments, insights, discoveries start with asking questions and fundamental science. And it was a 50-year route to change the world, from fundamental science to modern society. Wasn't it in the late 40s and early 50s that chemistry made the liquid crystal materials and physics the transistors? Then engineers came to make devices, computer scientists, many others contributed. Nobody in the early 50s knew that we were going to build a smartphone. The word did not exist. We were just building the first computer. It was in 1980 that the first lithium batteries were made, that made it possible that we have pacemakers, that we have electric cars, that we can power our smartphones. And it was last December that John Goodenough got the Nobel Prize in chemistry for the lithium battery. Let's not forget that. We also cross borders of disciplines, borders of countries, to work together to make this all possible. And this is the way to the future. A long journey to the future. I come from the Netherlands. You all know where Europe is, and where Amsterdam is. And 200 kilometers northeast of Amsterdam is the city of Groningen, which is an old city, more than 1,000 years old. The university is more than 400 years old. We are quite proud of that. And we have a very strong cooperation with Bandung. Many students exchange. There's cooperations already for many years, and we enjoy that a lot. This is where I grew up, in a tiny village on the German border in the northeastern part of Holland. I think hardly anybody from the village ever went to a university. These are my parents. And this is my brothers and sisters. My younger sister was not born yet. 9 brothers and sisters. We had not many, were not very rich, but my parents made it possible that we go to high school and then to university. I think my adventure in the unknown, to learn, to know, started already at the farm. When I asked my father, how is it that this flower can be red and the other is white? How is it that from a tiny seed you can grow rice or wheat that feeds you? I was lucky that I could go to a high school, and my teacher, op de Weeg, my chemistry and physics teacher, was an extremely inspiring person. And I was good in mathematics and physics and chemistry, but he made me so enthusiastic for chemistry, doing experiments, making beautiful crystals, colors, ugly smells. We enjoyed, and I wanted to become a chemist. And this is when I went to the University of Groningen, and I studied with Professor Winberg. It was mentioned before. He was American. He was my PhD supervisor. And when I was 20 years old in his group, this was my first new molecule I made. Can you imagine? I came to his office, and I said, I made the molecule. And he said, Ben, nobody in the world ever made this molecule, not even in America. I was so proud. It was absolutely useless, but I was so proud. It's like a young man or a young girl making her first poem, piece of music, or make a goal in a soccer play or so. I was really proud. And so I want to give credit to our teachers, because the teachers open windows. That's what we do at universities and our schools, and they deserve that they shape our future, the future of the young people. Let's not forget that. That's our task and our duty. After my studies, my PhD, I went to work for Shell. So I went out of the university, and that was a really great experience. Out of the comfort zone of the university to work in a big company, to learn about how to make practical things that can help to build industry. And I worked in Amsterdam at a big research laboratory, and then I moved to England in the biosciences laboratories. And then I went back to the university because I wanted to work with the young people, to train them, to educate, and to do research. And so I am a chemist, and I developed a passion for molecules. I wanted to design my own molecular world. So the art of building small, we are building molecules through chemical synthesis in the laboratory. We invent new reactions, new materials, and I want to talk a little bit about that. So why are we doing that? We do this in the laboratory, things that never existed before. We want to make them. Maybe because we enjoy the beauty of these molecules. More often, of course, we want to test a theory to find out if you can make something. Test a theory of chemistry, physics, biology. But we should not forget our heroes. We could not do anything, wasn't it, for our common language. This is the language that we have, the language of the atoms, the periodic table, the atoms of the molecules. And it was this gentleman here, this one, sorry, this doesn't work very well, this one here, Dmitri Mendeleev, who discovered the periodic table. Can you imagine? He made the rules how you connect every atom, every molecule, the relation in the whole universe. Everything around us, all the materials, every atom in your body, your own body. I think he belongs to the category of Newton and Einstein that you certainly recognize here. So it's thanks to Mendeleev that we know now this is our formula of the human body. Hydrogen 375 million, oxygen 132 million, carbon 85 million. It goes on and on. One lonely molybdenum. Cobalt, sorry. Robbie, can you stand up for a second? This gentleman did his PhD in Groningen and he was in my group. He is now a young professor here. He is a great talented man from your country. Look at this guy. He is more than 60% water. That is why there is so much hydrogen and oxygen. But he looks okay, eh? A few other molecules do the job. Great, you can seat it again. Thank you for it. So this is how we know our body, how we work. So we do chemical synthesis. Sorry. We do chemical synthesis in the laboratories. We build molecules and materials. We have a universal language. When I go to Indonesia or to China or to America and I talk with the students, they all will understand that this is molecules because we have a common language, despite the fact that we don't speak each other's language maybe. We have no borders. There's a lot of talk about borders. We go beyond frontiers. That is the mission of the university. International cooperation and a passion for discovery. So we build molecules, and people ask me always, how do you build molecules? We start with simple molecules, and we build step by step more complex molecules in the laboratory by breaking chemical bonds and making chemical bonds. What you see here is a very complex molecule. This is Taxol. It's used as a drug in the hospital against breast cancer. It takes many, many chemical steps to make it. And you have to do it with great precision. Otherwise, of course, it is not a pharmaceutical. Otherwise, you cannot help. It cannot be used in your body. So we make very small molecules, like ethylene. 2 carbons and 4 hydrogens, which is the basic for plastic. 160 million tons a year all over the world. We can discuss later about the problems of plastic, because we have to do something there. Or we make very complex molecules. Look, vitamin B12, carbon, hydrogen, nitrogen, oxygen, phosphorus, cobalt, 35 tons a year all over the world. Very small amount. Why? You need only microgram quantities of vitamin B12 to stay healthy. Hugely complex, very simple. So we make drugs, pharmaceuticals, cables and cars, all the components of your car, including the fuels, soaps, your smartphone, clothes. Not in isolation, of course. You make the materials, the molecules, and then you work together with material scientists, engineers, etc., industry, to build all these products. This is what we are very good at. Seeing all these things around us, making modern society. But what we are not very good at is making anything that moves. The fact that I can walk, that I can talk to you. Look, your body, a living organism, is full of moving machines. It was mentioned already. The ATPAs, rotary motor, that makes the fuel in your body. The motors that walk, that make it possible that things are transported in your cell. Look at this one. The ribosome is the protein building machine. It's a complex robot in your body, millions and millions of them. The bacteria flagella motor, you see it rotating? This makes the bacteria swim in your guts. The process of optical switching in the eye. This is nanoscience in your body that makes it possible that we are alive. And it was Richard Feynman in 1959 who said, there is plenty of room at the bottom. What he means is going smaller and smaller and smaller to the size of molecules. Technology at the size of molecules. You see here the first computer there under his picture. That filled half this room and could do way less than your smartphone nowadays. And then it went smaller and smaller, and the professor mentioned already, 20 nanometers. I think we are down to 12 nanometers nowadays. That is top down, but what we want to do is bottom up, from small and building larger. And I had the privilege, 50 years after Feynman, to go with Fraser Stoddart and Jean-Pierre Sauvage, and I got this call from Stockholm. Because we built tiny machines, and I want to tell you a little bit about it. But before, let me put it in perspective. 1 nanometer, ladies and gentlemen, 1 nanometer is 1 billionth of a meter. If I take one of my hairs here, you see? Can you see it? No, it's too small. One hair, the cross-section of a human hair, is 80,000 nanometer. It's very big in our world. Does size matter? Yes, of course, you know. When you go to a pebble beach, these stones, you don't drop there, because it hurts. But when you go to such a sandy beach, it's so beautiful. It's the same material, just a matter of size, smaller. So nowadays, you can buy nano products, like, for instance, Nano Sensitive, which is a cream. It feels so good. It's also a bit expensive, but it's really good. And you see quantum dots, 6 nanometer, 2 nanometer, you get these beautiful high definition screens, very high, nice colors. This is nanotechnology that is already used these days. But these are hard materials. What we want to do is making soft things, like in your body, like the machines in a living body. So we started with switches, and I want to show you this morning a few of our discoveries. First, switches. This is how we started many years ago. To look at your eye, and in your eye there is a switch. The fact that I can see you and you can see me is simply due to millions and millions of switches. Like you switch on the light, like you switch on the car. But now, molecular switches. This is the molecule. You switch from this form here, you see a band structure, to a more linear structure over there. That is what happens in your eye when we see each other. And it should switch back and forth. So we thought, when I started, can we make a computer or do information storage at the nano scale? Look at your eye. Nature does it. Information we can see. So we built artificial switches. You might say, why not using the system from your eye and build a computer? That does not work. It is easy destroyed. You have to make much more robust systems. So we built artificial systems. Look at the molecule. That's not so. We built these systems where we could do exactly the same as in your eye. Switching 0, 1, 0, 1, 0, 1, 0, 1. And then we make materials for information storage. And you can see, you can make a compact disk. And you can store information. 0, 1, 0, 1. This is what we did together with Philips company. We make plastic where you could write with a laser information. And you can see with one compact disk, you can store these megabytes that you can see there. What does it mean? If you can write information at the molecular scale, nanotechnology, you can have one compact disc, one CD, and you can listen to music 240 years continuously. Your grandparents and your grandchildren can play for 240 years music without stopping on one CD. Of course, it's not good for the music industry. But this is the potential of nanotechnology. It has not been realized yet, but we can make switches where we can switch back and forth and store information. But then we thought, more recently, let's look at another problem. We all know that when you take a medicine, that you want to have a medicine that is active, that does something. If the doctor prescribes you a medicine, you hope it does something, eh? It works. We want to have precision therapy, to switch a medicine on and off. So what we did is, we have a medicine that is off, and we switch it on with a nano switch, a molecular switch. Can we do precision therapy? You imagine you have an infection here. You get an antibiotic. You all know you have a lot of problems with the bacteria in your guts, etc. But if you can switch it on here, precisely on the spot, you can do maybe precision therapy in the future. And your other bacteria in your body will not be harmed. That is the idea. So we work on two important problems: bacterial resistance. Now we are all very much afraid of coronavirus, which is a serious problem. But bacterial resistance was called by the World Health Organization one of humanity's ticking time bombs. Why? Because resistance built up and we have not enough new antibiotics. And many people around the world actually die. Think of tuberculosis and many other infections. So if you could make precision therapy and it switches on, and after 12 hours, for instance, it switches off, the bacteria don't build up resistance, you have precision therapy. Cancer treatment. Everybody knows when you get a chemotherapy, yeah, you get a lot of serious problems. So what if in the future, with new imaging techniques, where we and many groups work on, you can find these tiny tumors and then irradiate with a laser and activate your chemotherapeutic agent exactly on the spot where it's needed. No side effects in the rest of the body. That's a dream. Not yet. But in the near future, maybe. We are working on that, together with many groups around the world. So just to give you an example, look, we take an antibiotic, it's off, 0. We can switch it on with light, and if this antibiotic is active for 6 hours, then it's off again. No bacterial resistance buildup. Switching on with high precision, addressing with a laser. You can see here, you will appreciate, we grow here bacteria. The biochemist will recognize you grow bacteria, and you can see we grow bacteria as a yin-yang figure. Where there is light, the bacteria don't grow. Where there is no light, the bacteria grow. We can switch on and off bacterial activity. But there was one serious problem, and that is how to get light in the body. Because you don't want to use ultraviolet light, eh? It's dangerous, eh? When you are too much in the sun. So we have to use red light. And the students worked hard to use red light, because red light can go very deep in the body and is harmless. And so my student made a switchable antibiotics with red light. And this is his hands. You can see the red light goes straight through the fingers of my students. Why do I show this picture? Because the joy of discovery brings arts and sciences closer together. Imagination and creativity, that's what we need to come up with the original discoveries and inventions. And that's what we try to do at our universities. I enjoyed that there were photographers, artists from all over the world that came to visit laboratories, and they also make these pictures of the hand of my student who made the discovery. And it's now in exhibition. Sorry, this is in Dutch, but it was in exhibitions, arts exhibitions. I want to emphasize, enjoy the beauty of science. So, let me talk a little bit about molecular motors, because I was talking about switches going back and forth, 0, 1, 0, 1. But that's not a motor, eh? You have to build a motor. Why are there motors in your body? There are millions of motors. Why are they there? Of course, to make possible that I move. But also, I sometimes see on television, or I read in newspapers, be in equilibrium. Please, please, don't. Be in harmony or in balance. That is important. But don't be in equilibrium, because a living organism is not in equilibrium. If you are in equilibrium, you are dead. These motors and machines push your body out of equilibrium all the time. That's why all these machines are there. So this is the most important motor in the world. It was mentioned before. This is the ATPA's rotary motor. You see it spins, it rotates. In your body there are millions and millions of these motors. You might think in your car there is a beautiful motor. This motor, this nano motor, is way more beautiful. You know what it does? It produces almost half of your body weight of fuel every 24 hours. Can you imagine? If you are 80 kilograms, it produces almost 40 kilograms of fuel every day. You don't eat 40 kilograms every day, eh? Even if you like Indonesian food a lot, like I do. This is all recycled. Can you imagine all these millions of nanometers make almost half your body weight every day and recycle everything? We talk a lot about recycling, one of the big challenges for the future. How to recycle our materials. Come on, why can we not recycle? We are not smart enough. Our body does it all the time. Half your body weight. So what is key? Look, how to control, to make a motor, it's important to control rotary motion and to control left and right. This has to do with stereochemistry that was mentioned. Imagine you are in your car and there is equal probability going backward or forward. You know where you get? Nowhere. You stand still. Either you go in this direction or you go in this direction, right or left. And that's a bit of a problem because we have to distinguish between left and right. How do we do that? Again, in Mother Nature, we have this left and right-handed molecules. That's a signature of life. Like the DNA, which is a right-handed helix. It was called the Mona Lisa of modern science. And I think we all agree on that. So what we did is, we built these tiny motors that were either left or right-handed. So they go clockwise or counterclockwise. And they are powered not by petrol, but by light. So this is the first molecular rotary motor in the world. It's about 1 nanometer, 1 billionth of a meter. You see it rotates, and the energy comes from the light. It's a light-driven system, powered by light. You see it also rotates in one direction, eh? We can also make it rotating in the opposite direction if we make the mirror image, left or right. That's how we build it. Now you might ask, that's nice, academic research. Of course, we were extremely proud because for the first time we could make something that could move. This does not move. This does not move unless I move it. Yeah? You don't move unless your motors make it possible that you can move. So now we have something that can move. So we can move, rotate something. We make this kind of movement, this kind of machine type function. Here my students were inspired by the movement of the moon around the earth. You all know, my students like to look at the moon. Maybe they are very romantic. No, more important, you realize when you are on the moon, you always see the man on the moon from the same face. It's connected, synchronized rotation. We build it at the nano scale to build tiny machines. My students also took this material from your smartphone, put in a molecular motor, put a glass rod on top of it, and then you see it spins. This is a soft material that's in your smartphone. You know when you push, if you push on the screen of your smartphone, that is soft material. Don't push too hard, because you destroy your smartphone. That is soft material. That's the liquid crystal of your screen, the TV, your computer. And you see, we can use that material and make it moving with our molecular motors. So now we have surfaces that can move, that are responsive. I'm from the Netherlands, so we like windmills. So we build all, you see this is a traditional windmill, this is a modern windmill. We built a nano windmill. You see the legs, the rotors, and we built a nano windmill park. Our ancestors 500 years ago built these windmills 20 meters. We built them 1 billion times smaller, 2 nanometers. So we have now a surface completely covered with windmills. They are powered by light and they move. So we have a surface like this. There's a layer of these tiny mills and they all can move. Why do we do that? Is that just for playing with our students? Is that what university professors do in the Netherlands? No, of course not. Because we want to make responsive materials. Think about the future. Self-cleaning surfaces. You don't have to clean your glass anymore. The solar panels, the dust on the solar panels removes itself. Your car cleans itself. When you have a scratch in your car, now you have to go to the garage. If you have a scratch in your finger and you are healthy, it repairs itself. Now people make materials, when you have a scratch, it repairs itself because they are dynamic responsive. Light comes in or air and it can be dynamic and it can respond. This offers tremendous opportunities for our material scientists, our engineers in the future to make the materials of the future. We also build a nanocar. My students actually were a little bit jealous because the engineers, many of these engineering students go to Australia where every year in September they have an electric car race. You see these electric cars with solar panels? So these engineering students, they build these electric cars and then many countries come together and they have this race 3,000 miles through the desert. And my students say, can we also go to Australia? I say, look, we are molecular architects, molecular engineers. We cannot do that. So, but let's build a nanocar. So you see, we built a 4-wheel drive nanocar. 4 of these motors power it. And it's not 2 meters, but it's only 2 nanometers, 1 billion times smaller. Of course, you might ask, why do they build these nanocars? You see, the scientists, we want to prove that you can go from rotation, to forward movement, like I do now. That was, of course, the scientific question. But we built this car, here it is, and now I have to warn you, in your body, there is many of these machines, they don't, a car at the nanoscale moves a little bit different from the car on the road. You see? It's like this, it's stepping. It's like if you have your muscle, all these millions of motors that make this possible, they walk like this. So this is the real nanocar there. You can see 2 nanometers in size. And it moves. Just to make sure that you realize that this happens in your body, you will see this movie now that I borrowed from Harvard. You see, when a car or something moves in your cells, the highway from here to Jakarta is built. When the car passes, it's detached, When a new car comes, it builds a new highway. It's all dynamic. This happens now millions and millions of times in your body. Look, they built, they disassemble. This is how things are transported in your cell. Millions and millions of times at this moment. That makes it possible that you are alive. So you all know, oops, what happens? Okay, this is a modern electric car, a Tesla. And I think we will all in the future have electric cars. This is our car, our nano car. You see this powder there? Tiny powder? This is 1 billion times 1 billion nano cars. 1 billion times 1 billion. My student's car manufacturing plant is not so bad after all, eh? Ladies and gentlemen, it took us 8 years to build a nano car and to prove it. Science sometimes takes time. Yeah? You make failures, you have to start again. A PhD study in Holland is 4 years. You remember, I promised my students, when you build the nano car, you can go to Australia to a chemical conference. I will pay. The first generation never made it because it took us 8 years to build it. But at the end, we did it. There was also a nano car race. You see, Formula One. It was in Toulouse in 2017, the first ever nano car race in the world. It's more for fun, you know, to show that you can move something. I want to show you one other example, because people ask me all the time, can these things move in my body? And I said, of course, I mentioned already the problem with getting light in the body, etc. So we discussed with the students again, can we make a kind of nano submarine that goes through your blood vein, that the doctor can inject to do a repair or deliver a drug? But then we had the problem, what is a good fuel? And then we discussed and we thought maybe sugar, because there's plenty of sugar. So here what you see is a nanotube. You can see it moving there. If you see it moving there. Yeah? These are tiny spiders of nanotubes that move autonomous. I don't have to do anything. It's just sugar, water. And you see these bubbles? That's oxygen. And then we know that it works. So this is biocatalysis. We put this biocatalyst on the nanotubes. They convert sugar, they eat sugar, and propel these nanotubes autonomously. We don't have to do anything. Just add sugar water. This has no application yet. This is very fundamental nanotechnology. But you see, we can make things moving. And some of the elder generation might remember Fantastic Voyage, where they make a spacecraft the size of micrometer, and it was put in the body to go to the brain to do a repair. Will we have nano robots? There's a lot of talk about robotics. Robotics will change our society. Will we have nano robots? Is it science or science fiction? Will the doctor inject a nano robot to deliver a drug, a pharmaceutical, precisely where it's needed? Or do a repair? Or detect a defect in your body? I don't know. Not now. But we can move. We can make the first steps. You have seen rotation, translational movement. We can make this tiny submarine. Maybe 50 years from now, like think about the smartphone. Think 50 years from now, the doctor will inject a nano robot in your body, and it will look for a tumor and repair it. But I'm not so good in prediction. Like many of us here, I'm a scientist. And the best way to predict the future is to invent it. And that is, ladies and gentlemen, distinguished professors, that's what we try to do, all of us, together with our students. New insights and new discoveries. I want to finish with a few slides, if I'm allowed. Let me first emphasize, I started to look at Mother Nature, the flying bird, and your eye. We make switches and motors. We can make smart drugs, responsive materials, molecular machines, maybe robots in the future, and a lot of other possibilities. That's just a glimpse of what is possible in the future. We are just at the start of many new technologies. And so I could not have done anything, wasn't it, for sharing a passion with all these young heroes, the students, the researchers that make it possible. You see, there's also a lot of girl power. Inventing our future. And we need it. And I want to give a message to the young students, because I often get the questions, what is a good advice? I would say, follow your dreams. Be confident. Of course, there will be often failures, but that's normal. Discover your energy. What is your passion? What gives you a lot of energy in the evening? And discover your limits. How high can you set the bar? Don't always take it too easy. Sometimes you have to do something difficult, and then you are very proud that you accomplished it. An adventure in the unknown. It was for me when I was a student. It is for all the young people here. But most important, to discover your talent, follow your dreams. Everybody here has his or her own talent. Follow your dreams. So we are facing a lot of challenges. How to reduce CO2 emission. How to recycle our materials, I mentioned it already. How to feed 10 billion people. How to fly without kerosene. There's a lot of challenges for all of us to discover the future. But don't be afraid, because it was Francis Bacon who already said somewhere in the 1600s, there are ill discoverers that think there is no land when they can see nothing but sea. So you might ask, when I was a small boy in this rather poor farmer's family with 9 brothers and sisters in this remote village where nobody went to the university, did I ever knew that I would get a Nobel Prize? No, of course not. I was not thinking about it. I was working, I was teaching, I was doing research. When you go to the Olympics in Tokyo this year, you know what these sporters do? They not always dream about a gold medal. Of course, you dream sometimes. But what they do is they get up at 5 o'clock, train very hard, work hard, and maybe when they are very talented and they are lucky, you need also a lot of luck, they get a medal. I was confronted for the first time in 2011 when a colleague from the United States called me and said, Ben, that was in 9 o'clock in the evening, you were on American television. I said, come on, you are joking. No, you were on American television, The Simpsons. You see, The Simpsons predicted the Nobel Prize. You see, chemistry, Czar, Mörner, Virniga, Shonakashira. Murray got the Nobel Prize in 2014. I had to wait another 2 years. So the next morning, this was in the evening, the next morning, all my students came and said, Ben, you will get the Nobel Prize. I said, Nobel Prize? Yes, predicted by The Simpsons. I said, I'm fine. I don't need a Nobel Prize. The greatest honor that I ever get, I get a great honor today, but the greatest honor that I get nominated on American television by The Simpsons, this is the best you can get. But then, of course, I had to wait another 2 years, you see, and I had this event in Stockholm, which was like a fairy tale. You see the queen, the king, and the princesses, and this is the committee, and I just got my Nobel Prize. It was absolutely fantastic, and it was indeed a dream. Then we had a nice dinner. You see, we get a dinner for 1,200 guests. I'm sitting in the middle there somewhere next to the Queen. And then we had a celebration at the Imperial Palace. You see the king, my wife, and myself standing between the king and the queen and the princess. It was absolutely fantastic. But then I gave now, after this Nobel Prize, I go to schools a lot, elementary school, high school, and we had invited at our university several students, 400 from elementary school, 400 from high school. And then they said, what should we give him to? I spent the whole day with these kids, and they wanted to give me something. And they said, we cannot give him a medal because he has already a medal, got in Stockholm. How do they do this in America? You know, America is big, Holland is small. So in America, so you see Fraser Stoddart, he is in Chicago, Northwestern University. And in front of the university, chemistry department, there is this big reserved parking for Sir Fraser Stoddart, 2006 Nobel laureate in chemistry. 2 permits, you see his limousine? 2 big parts, just in front of the building. But in Holland, now they said we have a problem. Because Ben never comes by car. He always comes by bike. So now you see in front of the chemistry department, there is this small plaque, this size. And it reads, bicycle parking space reserved for Nobel laureates. So that's where I can bike my space. This is how we do things in the Netherlands. I want to finish with thanking you again, once again congratulating the university with this celebration, with our friendship and cooperation, and with the great honors here today. I also have to thank my family. This is where I grew up. My brothers and sisters, this is when our daughters were very young, and I worked way too hard, so I owe a lot to my wife, who made it possible that they grow up, they became students themselves. So I have to thank them. And my wife said, when a journalist asked them, how is it to be married to a scientist? And she said, being a scientist is a way of living. So my final slide is this one. The joy of discovery. Leonardo da Vinci, 500 years ago, said, where nature finishes producing its own species, man begins with the help of nature to create an infinity of species. This is what our scientists, engineers do, to build a new society. And for the young people here, all the students in the audience, imagine the unimaginable. Thank you so much.
Selanjutnya, sesi tanya jawab akan dipandu oleh Dr. Robi Ruswanda.
Question and answer session moderated by Dr. Robi Ruswanda.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Robi Ruswanda. I'm 60% water. I will be your moderator for this discussion session. I will pick 3 people, I guess, from the audience, from that side, in the middle, and this other side. And then please come to the microphone and state your question. You can ask, I already got one from the middle.
You can ask also question in Indonesia. He will translate.
Yeah. bisa tanya dengan bahasa Indonesia. I will translate it. One.
Yes.
Okay, let's just start with one. Okay, go ahead.
Microphone, please, that everybody can understand.
Assalamualaikum warahmatullahi wabarakatuh. dan selamat siang. Mohon maaf sebelumnya, saya pakai bahasa Indonesia karena takut salah.
No, let me say there are no stupid questions. Ask whatever you like. It's now the opportunity. I enjoy discussing. Please ask questions.
Hal yang saya tanyakan adalah pasti natural bagi semua manusia, terutama saintis, ketika dalam melakukan penelitiannya dan penemuannya bakal ada stuck atau bakal ada kayak momen ketika down gitu, ketika penelitian terus gagal dan bagaimana Profesor Ben menangani hal itu begitu sampai bisa menemukan mesin molekul tadi. Terima kasih.
Yeah, thank you. Your name is?
Naufal Hanif dari FMIPA.
Oh, Naufal Haris. Yeah, so the question is how to cope with failure and failure. How do you cope with failure?
When you are a scientist, you have to be able to deal with excitement, as I said, the joy of discovering something. But of course, there are many failures and uncertainty. If you cannot handle uncertainty, we don't know what we will discover tomorrow or next year. If you cannot stand failures, maybe you should not be a scientist, because this is inherent to science. If we would know everything, we shouldn't do it anymore, because we know it. But we scientists, we want to discover, to do new things. Yes, in all disciplines, new insights, new discoveries, new inventions, etc. And of course, we have many failures. Often, we are wrong, as I said. We have to deviate, to go a different route. And yeah, you have to take encouragement from the fact that every tiny step, every small new insight will help you on the way forward. And that will help our society. Yeah, sometimes you also have to sit back a little bit. Yeah, it's of course good to work hard, but I always say not only work hard, but work smart. Think about what you are doing. I remember when I was a PhD student, I know many PhD students and students sometimes struggle with this question, that things don't work, things go wrong. When I was a PhD student, I worked for 8 months on a project. Everything failed. I remember I came back home to the farm. My mother said, "You look terrible. Do you eat properly?" No, I was working harder and harder because I thought I had to accomplish it. But we were on the wrong track. So I took a few days off with my friends. We got a completely new perspective, started again. And within 3-4 weeks, everything worked. Sometimes it's also good, to rethink. But failure is part of it, yes. But the most important thing is we learn a lot from our failures. If you go in this direction and there is a dead alley, maybe you have to retreat a little bit and then, you can go out there. That's the best way. This is what we have to learn. And we don't know always what is the best route forward. So don't be too afraid, take courage and learn something from your failures. That's my message.
Yeah. Thank you, Ben. Are there any other questions? Come on.
Please. Yes. The lady there.
Wait, sorry. You have it, Ben?
Yes.
Okay, please go down.
Okay.
And Ben? Sorry, Ben. While waiting, there's another lady. Okay, yeah, there is closer to the microphone.
Assalamualaikum warahmatullahi wabarakatuh. Hello, Professor Ben. My name is Sophie Damayanti. I'm the lecturer from School of Pharmacy ITB. So my first question is, how do you find ideas? I mean, as lecturers, usually students come to you and ask you as supervisor, and then they ask what we should do for the research. So I ask, where is the source for the ideas? This first one. The second one, second one.
Yeah, sure.
Second one,
joke.
besides the Simpson prediction, as you mentioned, I want to know what were you doing when you heard the first time that you got the Nobel? Were you at home or in the university, or were you biking and so on?
Oh, yeah.
Thank you.
Yeah, that's a good question. Now, first, let me answer the first question, you know. That was about how to get to ideas. And of course, there I have some idea in which directions we want to work. I'm not a writer, I'm not a medical person, but we work on molecules. So we try to design new chemical reactions, new molecules that are either new drugs or new materials or new catalysts for the industry. We work also a lot together with industry. During my whole career, I had programs together with industry like Shell, AkzoNobel, and so these companies. So sometimes they come with questions and say, hey, can you do something in this area? That's one thing. Most of the ideas come because we discuss in the group, we read the literature. If you read literature, you know, like your recent literature, you think, oh, some people in Japan did this, but we have these molecules. Maybe we can do better, we can do different things. Often ideas come just because thinking about chemical problems in my case. So I often get also ideas on the bike indeed. I have to bike 15 kilometers to the lab, so that takes almost an hour. That gives you a bit of time to think. But many ideas come when you discuss with your students. So we have a lot of discussions with the students on the blackboard, discussing about new ideas, etc. And often what I do is I challenge the students, yes? And say, look, this could be done, but if you have a better idea. Let me tell you the story of one of my Chinese PhD students, a small guy, you know, very smart boy. I had at the end of the day in the evening a discussion with him for half an hour. I said, maybe in the next step we should do this and that. Yeah, but maybe you should go to the literature, read a little bit. The next morning, 8:15 in the morning, I just had stepped off my bike. He came to me, Professor Ben, I have a better idea. I went to the blackboard discussing with him for half an hour, and indeed, he had gone through with the original idea that we had the evening before. He had gone through the literature, and he studied very well. I think half of the night, he was looking, and then he came up with an even better idea, yeah? And that was marvelous, and it worked so beautiful. And we got a beautiful publication out of that. So there's not one way, but try to be open-minded, be creative, and try to think, oh, I don't want to do exactly the same as somebody else. If the Americans do this, let me think. Maybe we can do it a little bit different, yeah? Thank you for the question. The other one, where was I when I got the phone call from Stockholm? That's very special. I was in my office discussing with two students, a PhD and a postdoc, about the project. I was sitting there, and they call you, the announcement is 11:45 in the morning. They call you at 11:45, 1 hour before. And I was sitting there discussing with the students in my office about a problem that did not work, a failure. It didn't work, we were stuck. That was about these smart pharmaceuticals, you know, that we could switch on and off. And so we just had discussed 3 options. And I remember the telephone rang, and I said, maybe we should first try option 3 in the next weeks, and if in the coming month we cannot get any further, we should try something completely different. Then I took the telephone, Stockholm, Nobel Committee. I sent the student out. Then, after 4 minutes, 3 minutes, the secretary of the Nobel Committee, he started to explain to me, congratulations, whatever. And he said, Dr. Veringa, are you still there? It's so quiet. Because I was completely in a shock. I did not know what to say. And then, yes, I'm there and I'm honored. And then he explained to me. And then he said to me after 10 minutes, okay, I will call the next one. But you have to stay on, we call you back in 15 minutes. Because you have to think about what you are going to say to television. Because we make the announcement and you will be live, yeah, directly called in the television of the Swedish TV and the BBC and so. So then you have to think. And you are not allowed to say anything, eh? The only thing I did is I called my wife, and I said, better watch live stream in half an hour. And then they called me, you know, back, and they made the announcement. I was in the lab, in the office, at that day. And that was a lucky that I was there, because I was supposed to be in Germany, because to give lectures in Germany. But then my daughter got her bachelor degree of the university, a bachelor diploma, that afternoon. So she said to me, you are not going to Berlin or München to Germany, because you will be there when I get my bachelor diploma, because you were not there when I made my first steps and I spoke my first words. Because you're always busy as a scientist, you know. So I promised her to be there. So, but of course, this ceremony was in the afternoon when I was on television and I had these interviews and so. So I never made it to the bachelor diploma of my daughter. My wife said, you were dressed pretty good, yeah? Because I had a jacket and a nice dress. And normally in the lab, you know, you don't dress up like that. And I said yes, because I had to go to the ceremony of my daughter. But I never made it. But she forgive me. It was a good reason.
Okay. Next question?
Yes.
Okay.
Yeah, please ask the question.
Okay.
Okay, good afternoon, ladies and gentlemen, and our honorable guest today, Professor Ferenja. First of all, it's an honor to be able to witness your inspirational speech in this very special occasion. Let me introduce myself. My name is Akbar, and I'm from the Faculty of Mathematics and Natural Science. And I have this one particular question. Well, from your speech, it's actually in line with me thinking that science and discovery is essentially joyful. Science is awesome. But there's one thing that stuck in my mind, that not everyone gets it. Not everyone thinks that discovery is joyful. Not everyone thinks that discovery is inherently awesome. They only think if it's practical, if it's useful for our life, then it is awesome. Then the other kind of science, I mean things such as pure science, discovery of a galaxy billions light years away, or smashing two protons together, they have no practical use in our daily life, I think. Yeah. And people think that those kind of things is actually useless. Yeah. Well, what I want to ask here is how to attract people to be interested and to be able to feel the joy of discovery.
Thank you. This is a very important point. Thank you so much. You know, of course, we all like to do something, some new insight, some new discovery, whatever, that can help our society. Being it a new drug to make better health, yeah? To make a new battery to make electric cars so that we have a cleaner environment, or to use less material, yeah? To recycle plastic. There are many, many things that we can do together with engineers, with many disciplines, with humanities, to build a better society. But we should not forget that we also should come up with new insights, new discoveries that we have no idea yet how they will change society. I mentioned the smartphone. Nobody knew 70 years ago that this transistor would make such a dramatic discovery. That we have now these beautiful screens, look, yeah? With these display materials and so. Nobody had an idea that we would discover that. They were initiated by people that enjoyed to think about the fundamental laws of nature, to see what is possible, what can we invent, what can we discover. And I think that is important. In our work, of course, we work at the university, and I'm working not in an engineering department. I have many colleagues that work in chemical engineering, yeah? So we have cooperation projects together with them. I work more on fundamental aspects, but don't forget, I work now together with the doctors in the hospital to see if we can use the smart drugs for the patients. I work together with industry to see if we can use the nanotechnology to make better processes in the chemical industry. And I'm extremely proud that my students made a discovery already more than 15 years ago that is used now in industry to make a chemical process for a life-saving drug. So they built the chemical process, the factory, on the catalyst that we discovered in our laboratory. So it was patented, of course, and industry developed it because you cannot do it all on your own. You need colleagues, engineers, process development. So we are not living in isolation. But to come back to your question, we should make clear to our leaders, to our politicians, to all the people, how important it is to educate, to train the young people to the future. And one of the best ways to do that is to confront them with the edge, the frontiers of our knowledge, and go beyond that. If I train the student for today, that's not a good job. I have to train them for tomorrow, for 10 years from now, because they will be the leaders of our society. They will do the innovation. That is, I think, an important mission of the university, to look forward, both fundamental and more applied, societal, industrial relevant projects. The whole package together, I think that is what we should bring forward. But don't forget the basis of bringing forward knowledge, inventions, discoveries, and to train our students to bring them to the future.
Okay. Thank you, Ben. I think we still have time for one last question. Okay.
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 Oh, many questions.
Let me ask.
You are the chairman. You have the choice.
Okay, the one is already in the, in
Okay.
the microphone. Please, one last
Okay.
question, I guess.
One question, please. Okay. Thank you, Professor Feringa, for such a beautiful and remarkable presentation this
Thank
morning. My name is Andrew Suhendar Natawigena. I'm graduate from the art and design from this university. So I would like to ask you about one question. It's very important. That where is a part of God in those remarkable process in this universe? Your presentation is very beautiful just now, and I would like, once again, to ask you, where's God in this process? Thank you.
Thank you very much. This is a very tough question. You realize, I must say, I'm a Roman Catholic, so I believe in God. Not everybody believes in God, but I believe in God. But you realize I'm a scientist. And a scientist, we can pray, yeah? And of course we can think about that what is out there, yeah? But realize we scientists have a mission, we teachers have a mission to take, you know, our knowledge and bring it forward to what I just mentioned before. I think if you bring it to God, I don't want to discuss about religion, you know, because we get in a completely different situation. But honestly, I think we all get a mission as human beings. And that is, God gave us talents. Everybody has here a talent, yes? Some will be musicians, architects, writers. Some will be a carpenter or a mechanic that repairs your car. I can tell you, we are nanoscientists, but I cannot repair my car. I'm extremely proud on the mechanic that can repair my car when there is something wrong, although I can build a nanocar. Somebody that can repair the roof of your house when it's leaking. Don't forget that. Somebody that teaches your kids in elementary school. Everybody has a talent, and I think God gave us the duty to take your talents and bring it forward for the benefit of our neighbors, our society, our friends, everybody. Yes? Apparently, I got a certain talent to be a scientist. Yes? You should be modest. When we were in Stockholm, yeah? No, let me say it a bit different. Of course, I get many requests because now they think as a Nobel Prize winner, you know something about everything. I think that's not entirely true. I'm a scientist. That's my mission. We are teachers and scientists, like many of us here, like the professors here. Yes? That is the mission God gave us, and we should bring that forward. Once again, I want to emphasize how important the talent is of every kid at every level. You don't have to do an academic study to use your talents. My wife was asked in Stockholm by a journalist on television, what is it? This, he must be very smart, this husband of you. You know what her answer was? You saw her picture with the 3 children. I was often away. See, her answer to the journalist was, it seems that he knows a lot about chemistry. For the rest, I'm a normal human being. Don't forget that. I seem to know quite a bit about chemistry, yes? My wife and you all know a lot, like about the rest of the things in the world. I think this is what I want to answer to your question, how religion comes into this. And of course, faith and religion is also very personal. It has to do with your own inner thinking and beliefs.